Hi everyone, myself Dr. Manjunatha C, working as an assistant professor in the Department of Chemistry, RV College of Engineering, Bangalore, India. In this video, today I would like to discuss about the doping, the importance of doping, functionalization, and how the properties are changing upon doping and functionalization, and what are the applications of doped and functionalized carbon nanotubes. We know that carbon nanotubes are one-dimensional materials, and they're completely made up of carbon, sp2 hybridized carbon, rolled up in the form of cylindrical tubes. Maybe made up of one layer graphene or two layer or multi-layer graphene sheets of different types. Maybe chiral shaped or zigzag shaped or armchair shaped. So actually, it is completely insoluble in water. Okay, since carbon is non-polar in nature, it is not soluble in polar solvents, especially in water. Okay, therefore, it limits its applications. If any material is not soluble in water, its applications will be very less, limited. So therefore, in order to enhance its solubility and polarity and all, so this carbon nanotube has to be substituted, structurally modified, means substituting some carbon atom with other atoms, or by attaching some polar functional groups. So in this video, I would like to discuss about, in the beginning, I'll discuss about doping, and then functionalization, properties, and then applications. Okay. So there are various types of carbon nanotubes in which they have substituted carbon by different atoms. Mostly they have substituted carbon by nitrogen atom. They're also called NCNTs, nitrogen doped carbon nanotubes. Why nitrogen? Nitrogen is because nitrogen is next to, it's neighboring to carbon, and it is a pentavalent, and its size is almost same. The size of carbon atom and nitrogen atom is almost same. Hence, you can easily substitute nitrogen atom in place of carbon in carbon nanotube. And also the electronegativity, it is almost similar. It's slightly greater. 3.04 is the electronegativity for nitrogen atom, and 2.55 is the electronegativity of carbon atom. So because of the substitution, the substituted site will exhibit different properties. Okay. So this carbon nanotube is having alternate pi bonds, means it is completely conjugated system. So when you substitute nitrogen atom will also retain the delocalization, that is resonance in CNT. However, there will be a lone pair of electrons which will be present on nitrogen atom. But in case of carbon atom, all the 4 electrons are involved in bonding, pi bonding or sigma bonding. When you substitute nitrogen atom in place of carbon, so nitrogen will have a lone pair of electrons, unbonded electrons. So it acts as a Lewis base. It can react with acids and all. Okay. So this nitrogen doped carbon nanotubes finds a large number of applications in all these reactions. All these reactions are involved in batteries and electrochemical water splitting, hydrogen production, etc. This is ORR reaction is a very important reaction in case of batteries and also hydrogen production. That is by splitting water. Oxygen reduction reaction is ORR reaction. You can see that this NCNT acts as a catalyst and provides the active surface for water splitting. Okay. For oxygen evolution reaction. It helps in oxygen evolution reaction in acidic medium and as well as alkaline medium. This is the image representing how the structure of CNT is changed when some of the carbon atoms are substituted or doped by nitrogen atoms. So there are varieties of active sites are created, like graphitic nitrogen atom inside the bulk, that red color one which is representing. This is the carbon atom replaced by nitrogen atom. So it is a graphitic nature only. The hexagonal rings are arranged, but however, there will be a lone pair of electrons on nitrogen atom here. It is bonded 3 bonds and retain 1 lone pair of electrons. And if the edge carbon is substituted by nitrogen atom, this will have different chemical environment as compared to bulk graphitic nitrogen atom. So there will be 2 different active sites. And also there are 2 types of rings are formed. That is a 6-membered ring and as well as 5-membered ring. So this is the green color one is representing the nitrogen atom substituted in place of one of the carbon atom. So therefore this ring is actually made up of 5 carbon atoms and 1 nitrogen. So therefore it acts as a pyridine. Means a benzene ring is replaced by pyridine ring. So this will have different chemical property and exhibit different properties, optical, electronic properties. Okay, and you can see that. And also there is a chance for forming a 5-membered ring like this pyrrole ring. This is the yellow color one. Is actually nitrogen atom, which is linked to only 4 carbon atoms. It leads to the formation of pyrrolic nitrogen atom. So there are 4 types: graphitic nitrogen atom, that is in the bulk, and graphitic nitrogen atom in the edge of the carbon nanotube, that is a 2-side edges, and pyridinic nitrogen atom, that is 5-membered ring, and pyrrolic nitrogen atom. So because of the creation of different types of active sites in the carbon nanotube, its properties are completely changed, completely altered. And you can see that you can see here, this is a very big ring is formed here like this. So the chemical environment is completely changed, and hence its chemical physical properties are completely altered. So therefore this is the effect of doping. Let us look at what are the procedure used for this doping, substitution of nitrogen atom in place of carbon atom. Okay, this can be carried out by 2 ways. One is in situ synthesis, or the other one is post treatment. In situ synthesis means while preparing this CNT itself, in the previous video I just explained chemical vapor deposition method we use for the preparation of carbon nanotube. So during the preparation of CNT in the CVD itself, by using another nitrogen source along with hydrocarbon, we can prepare this nitrogen doped CNT. We can use ethylene diamine, DMF, dimethyl formamide, imidazole, etc. So these are the nitrogen source they have used to dope nitrogen in place of carbon during CVD method. This is one way of preparing nitrogen doped carbon nanotube. Or the other way is first you prepare a CNT carbon nanotube, then you go for post treatment. Means again you take that prepared carbon nanotubes using ammonia and pyridine vapors, carry out the same reaction in an inert atmosphere at 800 to 1200 degrees centigrade. So some of the nitrogen atoms can be replaced by this nitrogen atom in that reducing environment. So these are 2 ways of preparing nitrogen doped carbon nanotube. One is in situ synthesis and other one is post treatment. Okay. And as I told you, this nitrogen doped carbon nanotubes finds large number of applications, especially in oxygen reduction reaction, which is one of the main reaction in metal air batteries, and especially fuel cells, and also water splitting reactions. Okay, this is about doping. Okay, next let us look at another aspects of CNT, converting a polar CNT non-polar carbon nanotube into polar carbon nanotube, that is by chemical and physical functionalization. Let us look at the functionalization of carbon nanotube. Despite CNT's exceptional properties, that physical, mechanical, optical properties, its dispersion into a matrices or solvents is the biggest obstacle in practice. Especially for drug delivery and all, you need to disperse the CNTs into a polar solvent. So this has to be converted to a polar by attaching some polar groups. So because it is not soluble in polar solvents. Let us look at how it can be converted. So that carbon nanotubes can be converted to soluble carbon nanotubes by two ways. One is by chemical or covalent functionalization, or by physical or non-covalent functionalization. It means that the carbon nanotube, the surface energy is different. Once it is, once the surface is attached with some polar groups, its surface energy is completely changed, and also its solubility towards polar solvent like water and other polar organic solvents will be easier. So therefore, the surface of the carbon nanotube is modified by attaching some polar functional group by through a covalent chemical bonding, that is called chemical functionalization, or it is also called covalent functionalization, or by attaching, or by without forming a bond, just by adding some metals into carbon nanotubes, or by covering the CNT with some polymers, just by physical functionalization, we can convert that carbon nanotubes into different moiety. So we know that CNT, carbon nanotube, is made up of only carbon. I'm not talking about doped CNT. I'm talking about pure CNT, in which carbon atoms are sp2 hybridized. When you go for covalent functionalization, means when you attach some groups to a carbon atom, that hybridization of carbon, that is sp2 hybridization of carbon in CNT, changes to sp3, and it loses the pi conjugation system, because when you attach some groups to a carbon atom, it forms 4 sigma bonds. Okay. In pure CNT, the carbon atom is having a 3 sigma bond and 1 pi bond, and that pi bond breaks down. That 1 pi bond breaks down, and it will attach to a functional group. Okay, this is the image representing 2 ways of functionalization. This is carbon nanotube, and this is insoluble in water, and it is non-polar in nature, and it has less applications in biomedical field because it is not soluble in polar solvent, and it cannot be used for drug delivery and other applications. This can be converted to a polar moiety by attaching some organic group. R is a functional group. You can see here there is a breaking of this function, what is that, delocalization. Here the sp2 carbon changes to sp3. It forms trigonal planar shape, change to tetrahedral shape, because it forms a 4 sigma bonds here. This is actually forming a real covalent bond here, that is called chemical functionalization or covalent functionalization. The other way is non-covalent functionalization, or just it is also called physical functionalization, means without destroying its hybridization and delocalization, you are just now attaching some polymers and some metals, so that it will stick to that just by van der Waals force of attractions. Okay, there is no covalent bonding here. Let us look at some of the examples in which how that CNT is converted to a different organic moiety. See, this is CNT. When you just heat it in a air at 300 degrees centigrade, carbon atom is getting, one of the carbon atom, the surface carbon atom is getting oxidized to carboxylic acid. Means it becomes carboxylic acid functionalized carbon nanotubes. Now, because of the presence of this COH group, this moiety is polar in nature, and it is soluble, and it becomes acidic. This is neutral, and this becomes acidic. See, just by heating you can convert its properties. Further, because of COH group, you can go for reacting with thionyl chloride SOCl2, and you will get acyl chloride, carbonyl chloride. This is another moiety, another organic, another functional group attached to CNT. And if you react that COCl functionalized CNT with amines, you will get amides. So we know that most of the amides are used for drug delivery. Drug molecules are it is used for the preparation of medicines and all. So this is the scheme 1 representing the chemical functionalization. Or scheme 2, you can see that just by adding nitric acid also you can convert carbon nanotube into carboxylic acid functionalized CNT. So these are the different routes to convert from one organic moiety into another organic moiety. They are completely different. They are structurally completely different. See, it is acidic, and this becomes basic in nature.
So you can convert acidic CNT to basic CNT, and you can convert to polar, non-polar, etc. So this is the advantage of covalent or chemical functionalization. Okay, so these are the other examples which are representing how that CNT can be decorated with various functional groups and drug moieties. You can have millions and millions of new different organic moieties attached to CNTs can be prepared by covalent functionalization. Let us look at non-covalent functionalization. In case of non-covalent functionalization, there is no formation of covalent bonding. Means you are not destroying the hybridization. sp2 remains sp2, the hybridization, and also the structure will not change. It is just physical attraction, the pi-pi interaction. Because of the pi electrons which are present in the CNT, you are just adding some metals. See, silver is attached. Silver metal is inserted in the carbon nanotube. This is just physical functionalization. Okay, or nickel. Nickel can also be substituted here. So there is no covalent bonding here. So like this, you can add the substitute, convert carbon nanotubes can be decorated with other metals and all. Some gold nanoparticles, silver nanoparticles can be inserted inside the carbon nanotube without forming any covalent bonding. Or some polymers, big polymers can be just wrapped on the surface of carbon nanotube. This is another example showing non-covalent functionalization. Or some surfactants. So because of pi conjugation present here electron, you can attach some negatively or positively charged surfactants can be decorated on the surface of this. Here there is no formation of covalent bonding. It is just attraction between the positive electron cloud of this CNT and positive part of the surfactant. So like this is a digital image representing the carbon nanotube decorated with polymer. So this is about functionalization of CNT, chemical functionalization and physical functionalization. Okay. Next, let us look at the properties of carbon nanotubes. Okay, this is we know that the carbon atoms present in CNT, they're entirely made up of sp2 bonds. Means they have alternate pi bonds, and it is highly conducting. So because of resonance and delocalization. And look at this length to diameter ratio. We call it as aspect ratio. Look at this ratio. The length is how much times more than its diameter. So this is the beauty of this CNT. Almost 13 crore times length, more length than it is having more length than its diameter. And look at the diameter, 3 to 9 nanometer. And lengths they have reported in, there are some reports in which they have prepared carbon nanotube in millimeter range. The length will be in millimeter range. It has extremely high Young's modulus. And this carbon nanotube can be electrical conductive or semiconductive. Or if you functionalize with some groups, if you just destroy the conjugation, it becomes insulator. That is the beauty of the CNT. You can convert conducting to non-conducting, non-conducting to semiconducting, etc. just by substituting or doping or some functionalization. It has very high electrical conductivity, almost equal to copper, and high thermal conductivity as high as diamond. It is 100 times the strength is 100 times greater than the steel, and its weight is 1/6 to its weight. Can act as thermal conductor and also thermal insulator. Okay, so these are some of the selected electrical and mechanical properties of CNTs compared with other materials. Look at this thermal conductivity greater than 3000. Look at it is compared nowhere comparable to copper, carbon fiber, and other similar materials. Their thermal conductivity is very much below than that of CNTs. That's why CNT is a wonderful material. Look at the electrical conductivity, almost equal to copper. See, 6 into 10 power 6, and it is also 10 power 6 to 10 power 7. Very, very high, equal to metals. Young's modulus 1.5. Look at this, all of them, steel and diamond. very less as compared to CNT. Tensile strength 15 to 150, but for steel and Kelva, the strongest material, even they are not nowhere near to that of CNT. So these are the other properties compared with carbon fibers. CNT, look at this diameter, it is very high, and this is the very, very thinnest material, CNT 0.05 micrometer. And density is also almost the same compared to the density of CNT is almost same as that of carbon fibers. Elastic modulus, very, very high as compared to carbon fibers. Tensile strength, very high. Thermal conductivity, it's very, very high, greater than 2000. However, in case of carbon fiber, 640, very, very less. Coefficient of thermal expansion, -1, -1.45 for carbon fiber. Electrical resistivity, very, very less, means is almost equal to conducting, but carbon fiber is insulating material. So because of its wonderful structural properties, carbon nanotubes and functionalized carbon nanotubes finds applications in almost all the engineering fields. Okay, in case of optoelectronic devices, it is used in field emission FEDs, and in case of batteries, it is used as electrodes, capacitors, and supercapacitor electrodes. As electrode catalyst support for fuel cells, PM polymer electrolyte membrane fuel cells, and hydrogen storage material in hydrogen fuel car, and electrically powered artificial muscles in which the CNT has been used, and electrocatalyst for water splitting production, that is for ORR reaction, oxygen reduction reaction. This is being used as a catalyst. It's used as an adsorbent for water purification, for adsorbent for toxic metal ions and the dyes and all present in the water, and also photocatalytic degradation of organic pollutants present in the water. And it's been used for sensor to test, to sense the heavy metals, gases, volatile organic compounds, and biomolecules. And very, very importantly, the CNTs are used as a drug carriers in biomedical field. Okay, so this is another slide representing its interdisciplinary applications. CNTs used in fuel cell, supercapacitor, microscopy, starting from engineering to medicine. This CNT finds its applications, finds its place. Okay, so thank you for watching this video. If you have any questions or clarifications, please contact me through this email ID. Thank you.